We can start.
Okay, thank you. Let's start. So recall that we are studying G-invariant valuations on a spherical variety. So let me recall some notation. We have a spherical variety acted on by reductive group G. So X is spherical. And we denote it by Y naught, Y sub naught. The open G orbit in X. And also by Y upper naught, the open B orbit, open Borel orbit sitting inside. This was our notation, and we'll use it. So we are in the course of proving a lemma about G-invariant valuations, which can be formulated like this. It was lemma 1 on the previous lecture. It says that a G-invariant valuation say V of the function field of X over the field of constants is uniquely determined by its restriction to the multiplicative semigroup, to the multiplicative group of B semi-invariant rational functions. And the value of V at such a function, B semi-invariant function of eigenweight lambda, is given by a linear function on the weight lattice, which I denoted by V bar. So this pairing of the weight lambda with the linear function V bar. What was done, what we did on the previous lecture, let me recall. What was already done. First, we did the quasi-affine case. A case where X is quasi-affine. And in this case, we had an explicit formula for the evaluation on the coordinate algebra of X. So for regular functions, if F is a regular function on X, it can be decomposed as a sum over some index I of Fi's. So it is a regular function on X. And these Fi's are projections of F to irreducible submodules in the coordinate algebra of X of highest weights lambda I. And we assume that we take only non-zero projections. So we assume that all these Fi's are non-zero. And in this case, for such an F, we have that the value of V at F equals the minimum of all values of V bar over these on these highest weights, minimum over all i's. So this was an explicit formula which recovered V from V bar. This is a quasi-affine case. And also what we did, we constructed, we applied the affinization construction. So we took an open G orbit in X. We realized it as, yes, question? No. We realized this open G orbit as an orbit in a projective space, and we took a cone over this quasi-projective orbit. So we denoted this cone, punctured cone, so cone with the origin removed. We denoted this cone as y0 hat. So we have this projection, projectivization, or projection map, whatever you call it. And this y0 hat is yet another spherical homogeneous space acted on by a bigger group, denoted G hat. So G hat is just a product of G and the multiplicative one-dimensional group K cross, which acts by scalar multiplication on this cone, y0 hat. We constructed an extension of V from the function field of y0 to the function field of y0 hat. So we extended V from y0 to y0 hat, getting a G hat invariant valuation on y0 hat. Of the function field of y0 hat. So this is what we did on the previous lecture. And now we can in principle reduce the statement of the lemma to the quasi-affine case by considering V tilde instead of V. But actually we'll go somewhat roundabout and apply yet another lemma, which will be useful for us also later. So that's why I'm going to formulate this lemma now and apply it to the question which we study. This will be lemma 3. Which we can also call the second approximation lemma. The first one was lemma 2, which was formulated on the previous lecture, the first approximation lemma. And the second approximation lemma says that given a rational function f on my spherical variety x, such that it has b-stable poles, with b-stable poles. Essentially, this means that it is regular on the open B orbit. Why not? Y upper not? So if you have such a rational function with b-stable poles, then there exists a B semi-invariant function, f tilde, a B semi-invariant function on X, such that the following properties hold. So first, the value of my given valuation V on F tilde is the same as on F. Secondly, for any other G invariant valuation V prime, the value of V prime on F tilde is greater or equal than the value of V prime on F. So for any G invariant valuation V prime. And the third property says the same about valuations corresponding to B-stable prime divisors on X. So let me write it like this. The value V sub D of F tilde is greater or equal than V sub D of F for any B-stable prime divisor D in X. Okay, so this lemma 3 says essentially that you can, when you study values of invariant valuations on rational functions of such special kind with B-stable poles, you can replace such a function with a B semi-invariant function. And the value of the given valuation will not change, and the values of other valuations can only increase. So this lemma. Yes.
The third feature of
Yes.
F tilde. Do we need the divisor D to be prime divisor or not?
Yeah, sure. Of course, D is a prime divisor because I'm speaking about a valuation corresponding to a divisor. So the valuation corresponds to a prime divisor. Yes, of course. D is a prime divisor, B-stable prime divisor. So we'll prove this lemma a bit later, but now let's first finish the proof of lemma 1.
I think we didn't yet prove lemma 2, right?
That's true. So first we'll prove lemma 1. We'll finish the proof of lemma 1 in a couple of minutes. Then we'll prove lemma 2 and lemma 3. This is my plan. So let's first finish the proof of lemma 1. First note that the open Borel orbit y upper naught is an affine variety. This is a general fact that an orbit of a solvable algebraic group is an affine variety. So you can see a proof in textbooks on algebraic groups. But actually, we'll see the structure of y upper naught in more details a bit later in my lectures.
What is y upper naught?
Y upper naught, let me turn back to the first page. Y upper naught is the open Borel orbit sitting in the open G orbit, which sits in X. Okay? So y lower naught is an open G orbit, and y upper naught is an open B orbit, because it's spherical, so such an orbit exists. Okay?
So y upper naught, not y upper naught hat, right?
Yeah. Y upper naught, just y upper naught, not y upper naught hat. Of course, you may consider y upper naught hat as well. But here I consider y upper naught the open B orbit on my initial spherical variety X. Okay? Now, since it is affine, as I said, the field of rational functions on X, which is the same as the field of rational functions on this open orbit, is just the fraction field of the algebra of regular functions on this affine variety y upper naught. Now, let's take, so we have a G invariant valuation V. Let's take yet another G invariant valuation, say V prime. Let V prime be another G invariant valuation different from V. Another G invariant valuation of my field of functions. Then we may assume that there exists a function f which is regular on y upper knot and such that v and v prime take different values on this function. Well, because since v and v prime are different, they take different values on the field of rational functions. But the field of rational functions is the fraction field of the algebra of regular functions of y naught. This means that v and v prime differ on some function which is regular on y naught. And we may assume without loss of generality that the value of v on f is smaller than the value of v prime. Otherwise, you can just interchange v and v prime. Then, lemma 3 so lemma 3 says that in this case, there exists a B semi-invariant function, some f lambda, such that the value of f lambda, the value of v at f lambda, is the same as the value of v at f, which is smaller than the value of v prime at f, which in turn is less or equal than the value of v prime at f lambda. Okay? So I just apply lemma 3 to the function f, which is regular on y upper knot, and this means that the poles of f lie outside y upper knot, because since y upper knot is b-stable, then this means that the poles are also b-stable. They lie in a b-stable closed complement of y upper knot in X. So we have constructed a B semi-invariant functions, a B semi-invariant function on which these two valuations differ. So the value of v and v prime differs.
So we have that the pole of f lies outside y upper knot, right?
Yes, of course, because f is defined everywhere on y upper knot.
Yes. So how does that reduce to the pole of f is B stable? I mean, out of nodes, there are many B orbits, not only.
What can be the poles of y upper knot? So y upper knot is a B-stable open subset in X. So its complement, and of course X is irreducible. Its complement is a B-stable closed subset. And it consists of finitely many irreducible components. Actually, all these components are prime divisors because the complement of an affine open subset is a union of prime divisors. We have proved such a lemma some time ago. So all poles of f are from this finite set of B-stable prime divisors. So maybe let me draw a picture for you. So you have.
I think we have proved the theorem that the space X can be decomposed into finitely many B orbits.
That's we didn't prove about finitely many B orbits. This is true, but we didn't prove it. But we do not need this actually. We just say that we have this open B orbit.
We prove that they have finitely many G orbits.
Yes, that's true. That's true. We proved that there are finitely many G orbits. So let's look at the picture. So we have the open B orbit Y naught in X, and the complement of this open B orbit is a union of finitely many prime divisors, because it is a closed subvariety of smaller dimension, and it is a complement of a affine open subset. It is a union of finitely many prime divisors, and these prime divisors, di, di's. So only the function f can have poles only along these divisors, right? There are finitely many of these divisors, and f can have poles only along them, and they are b-stable because b is connected and there are finitely many of them. They cannot be permuted by b, so they are b-stable. Okay, is it clear?
Oh, I see. Well, the finiteness of the number of divisors comes from what? I'm now a bit confused.
Well, the finiteness of the number of divisors is just the finiteness of irreducible components of an algebraic variety. So this the complement of the open B orbit is a closed algebraic subvariety in X, and it has finitely many irreducible components whose dimensions are smaller than the dimension of X. And actually, all these components are divisors because Y naught is affine. We have proved the lemma that the complement of an affine open subset is a union of finitely many divisors. We have proved such a lemma when we proved, I guess, when we proved the Sumihiro theorem in the course of the proof of Sumihiro theorem a couple of lectures ago.
Okay?
We proved that the complement of an affine open subset is the union of finitely many prime divisors.
Oh, yes. I think we proved that the complement of an affine open subset is the union of codimension one.
Yes, and codimension one, an irreducible subvariety of codimension one is exactly what is called a prime divisor.
Oh.
What is a prime divisor? Okay. So the picture is like this, like you see on the screen. You have a big open subset, Y naught, and finitely many codimension one closed subvarieties in the complement. Is it okay?
Okay. So why is the proof over?
The proof is over because we have found. So we suppose that we have two distinct valuations, two distinct invariant valuations. They are distinct on the whole function field, and we found that they are distinct already on a semi-invariant functions. So we found a semi-invariant function f lambda such that the values of v and v prime differ on this f lambda by this chain of inequalities.
Oh, so where do we use lemma 2? I don't see any.
Well, we didn't. Well, actually, we didn't use lemma 2 here. We used lemma 2 on this step, on this second step, when we constructed when we replaced a spherical homogeneous space Y naught by this quasi-affine spherical homogeneous space. But you are right that we didn't use this step directly in our proof of lemma 1, in our final step of the proof of lemma 1. But actually, so this affinization construction, the extension of V to V tilde, here we used lemma 2 on the previous lecture. So lemma 2 was used on the previous lecture to justify this extension.
Extend the G invariant value to G hat.
Yes.
No, to Y naught hat. But in the proof of lemma 1, we did not use Y naught hat, I think.
We didn't use it directly. So we did not use it directly because we did not use the affinization construction directly. So this second step was not used directly in the proof of lemma 1. But actually, this affinization, a version of this affinization will be used in the proof of lemma 3, as you will see quite soon. And we use lemma 3 in the proof of lemma 1. So it is somewhat tricky. But anyway, finally, we use lemma 2.
So lemma 2 is used to prove lemma 3. Oh, I see.
Well, yes. You may say like this. So finally, we did the proof of lemma 1, and let's prove lemma 2 and lemma 3. So let me first recall the formulation of lemma 2, what it states. Lemma 2, maybe it's better to turn to the next page. So lemma 2 says, lemma 2 from the previous lecture, which was the first approximation lemma. It says that for any valuation not necessarily G invariant, for any valuation V of the function field of X over constants, there exists a G invariant valuation V tilde of the same field, such that for any rational function f, there exists an open subset of the group G, such that for any element small g from this open subset, we have the following. So the value of v on the shifted function g applied to f equals v tilde of f. So this G invariant valuation V tilde approximates, in a sense, the initial valuation V, which is not necessarily G invariant. So let's prove this lemma. Again, we'll start with the quasi-affine case. So in the quasi-affine case, let's take first a regular function on x. So x is now supposed quasi-affine. Let's take a regular function on x and consider the linear span of its g orbit. So it is a finite dimensional vector space, which I denote by M, a subspace, a G-stable subspace in the coordinate algebra of X. Let me write that it is finite dimensional G submodule. And my valuation V defines a filtration on this M, a descending filtration. Well, it defines a filtration on the whole coordinate algebra of X, but we can restrict this filtration to M. So M is the union of subspaces, which I denote M greater or equal than C over all rational numbers C, but actually over the value group of V in Q, which is cyclic. And this M sub greater or equal than C is just the set of vectors in M on which V is greater or equal than C. So the notation is the same as on the previous lecture. But now everything is finite dimensional. So we have a filtration, a descending filtration of a finite dimensional vector space. And since everything is finite dimensional, we can consider the maximal value of C.
Yeah. So why is M finite dimensional?
Well, I already mentioned this is a general fact that if you have an algebraic variety on which you have an action of an algebraic group G, then every function in the coordinate algebra is contained in a finite dimensional G-stable subspace. This is a general fact from the theory of algebraic groups.
I mean, when did you tell us this fact? It is convenient for me to refer to my notebook.
Oh well, you mean on which lecture?
Yes.
Well, I don't remember exactly. Let me just formulate it right now. Maybe just wait a minute. Let me move this line somewhere below. So let me formulate the following fact. Even more generally, I use this fact even in a more general setting. So suppose we have an action, we have an algebraic group acting on an algebraic variety X, and we have a line bundle over X, which is also equipped with the action of G. So the action of G on X lifts to the action of G on this line bundle. Then this gives rise to the action of G on the space of global sections of this line bundle. And the statement is that for any section, for any global section of this G line bundle over X, there exists a finite dimensional G stable subspace of global sections containing this given section S. So this is a general fact from the theory of algebraic groups and their actions on algebraic varieties. I have no time to prove it, but you can look for the proof to the paper of Knopp, Kraft, Luna, and Wust, which I cited some time ago. Knopp, Kraft, Luna, and Wust. So you can find the proof in this paper. But this is very general. So you need not assume that X is spherical. You need not assume that G is reductive. Well, almost nothing. This is a very general fact. And here we apply this fact to the trivial line bundle over X. The sections of the trivial line bundle are just functions, just regular functions. Okay? Is it clear now?
Maybe yes.
Okay, that's good. So let's continue the proof of lemma 2 in the quasi-affine case. So we have this filtration. Maybe, yeah, okay. So we have this filtration. And since everything is finite dimensional, we can consider the maximal value of C achieved at this M, at this finite dimensional subspace M. So put C sub F, excuse me, put C sub F to be the maximal C such that M greater or equal than C coincides with M. So you have such a maximal number C, and if you increase this C, then the next term of the filtration will be a smaller subspace. Okay.
Hey, Professor, the group G in the fact should be connected reductive group, right?
Not necessarily. Any algebraic group, neither connected nor reductive. Okay.
So this max can be achieved.
Say it again.
So this max can be achieved, or it is just a super.
Yes, of course, it is achieved because everything is finite dimensional. So actually, essentially, this C ranges over the value group of V, which is cyclic. So essentially, this C ranges over a discrete subgroup of Q.
So it is a discrete group, right?
Yes. Essentially discrete, because for all other values, this M over greater than equal to C coincides with some of the subspace for the discrete subgroup of Q. Yes. So the picture is like this. Actually, the picture is like this. We have this this M. Let me try to draw this finite dimensional space M like this. Excuse me. So we have this M. And it coincides with M greater or equal than CF. And if you take the bigger value of C, so if you take let me say, so let me denote like this. The subspace corresponding to the bigger value so let this be how to denote it, M strictly greater than CF. So this subspace is smaller than M, and the orbit of F, the orbit of the function F, which spans the space M. This is a subvariety in M, which spans it. This orbit intersects the subspace where the value of V is greater than CF in a closed subset. So this picture gives us, so this is the orbit of F in this vector space M. And this is the intersection of this orbit with the subspace where the value of V is bigger. So it looks like this. And now we see that the intersection of the orbit GF with this smaller subspace is a proper closed subvariety in this orbit. A proper closed subvariety in this orbit. So we can denote by U sub F the set of those elements G in big G such that the G shift of F does not belong to this closed subset, does not belong to this subspace M greater than CF. This is an open subset in G. And we may put, so let's turn to the next page. We may put v tilde of f to be equal to this value c sub f. Then we have a map v tilde from the algebra of regular functions on x, well, non-zero regular functions of x to q, which satisfies the properties 1, 2, and 3 from the definition of evaluation. Well, why so? Because just essentially, let's look at the definition. Essentially, the value v tilde of f equals the value v of v at gf for all g in this u, in this uf. Because if you take g in this uf, then the g shift of f is not in the smaller filtration term. This means that the value of v at this function is exactly the value c sub f. So this means that actually, well, actually this property holds in this case. This means that to check the properties for the properties defining the valuation, the properties 1, 2, and 3 for v tilde, to do this, it suffices to check these properties for the shifted functions and the values of v. For instance, if you multiply v and if you take v tilde of f1 times f2, then it is the same as v of g applied to f1 times f2. So since for v you have this multiplicative property, the product is taken to the sum of values, then the same is true for v tilde, and so on.
So why is the equality v equals v tilde satisfied?
You mean this one?
Yes, yes, yes.
Well, because by definition you put v tilde of f equals to c sub f.
Yes.
And if you take g from this open subset u sub f, then the value of v at gf equals c sub f. So let me write it here, maybe.
M equals mc sub f.
So this implies that the value of v at gf equals c sub f. Okay? And therefore, this property holds. Therefore, this property holds. So, I just explained it in words that you can check that that this v tilde satisfies the defining properties of evaluation. But let me, so to trace all details, let me leave it to you as an exercise. So exercise, it is not complicated, it's actually easy. Exercise 1. So check it. And since we have this map v tilde on regular functions, which satisfies the properties from 1 to 3, it extends to a G-invariant valuation of the function field. Denoted by the same letter. Well, it is clearly G-invariant just from the definition, because since this property holds in this case, for regular functions, when you shift f by some element of g, you do not change this general value of v. So you just shift this open subset. When you shift f, you shift this open subset, but still on an open subset of a group, the value of v on this shifted functions will be the same. It will be still equal to c sub f. So this means that v tilde of f remains unchanged when you shift f by the group action. This is why v tilde is G invariant. So in general, for a rational function, if you take a rational function, not regular but a rational function, so if you take f, a rational function on x, then it can be, since we are in the quasi-affine case, it can be represented as a ratio of two regular functions, p and q. Let's take u to be the intersection of the respective open subsets of p and for p and q, which we defined previously. Then for any g in this u, we have that the value of v, well, maybe I'll write it here, the value of v at the shifted function gf, well, it is the same as the value of v at shifted p minus the value of v at shifted q. Now, since g is both sits both in up and uq, this is the same as v tilde of p minus v tilde of q, and this is the same as v tilde of f. So we have checked this property. This one, in lemma 2 for rational functions, not only for regular functions, but now for rational functions by this computation. So this was the quasi-affine case. And the general case is already easy. If x is not quasi-affine, then what we can do? We can extend v to evaluation v hat to evaluation over y naught hat. This is what we did actually on the previous lecture. Y naught hat is not necessarily invariant, but now v hat is not necessarily invariant, but now y naught hat is quasi-affine. So we can apply the quasi-affine case to replace v hat by v hat tilde, which is a g hat invariant valuation. G hat invariant valuation of the same field. And finally, we just restrict this v hat tilde. This arrow is by the quasi-affine step, by the quasi-affine case, and this is just restriction. We can restrict this g hat invariant valuation on this field to a g invariant valuation v tilde. So g invariant valuation v tilde of the field of functions. So let me maybe write just like this. It will be easier. So V tilde is just the restriction of V hat tilde over the field of rational functions on X. And this V tilde will work for lemma 2. So it will approximate V. So first, let me again repeat. So what we did, first we extended the valuation V on this field to the bigger field. But now we are in the quasi-affine case, and in the quasi-affine case, we approximate this V hat by G hat invariant valuation, V hat tilde, and then we restrict this invariant valuation to the initial field to get the approximated valuation V tilde for V. So this is how the general case is reduced to the quasi-affine case. And this finishes the proof of lemma 2. So now I'm going to stop the first half of my lecture, and I'm ready to answer your questions if you have any. Let me say that these lemmas are technical, and so the whole lecture and maybe part of the previous lecture is quite technical, but these technicalities are indeed necessary to proceed in the classification of spherical varieties, which is our ultimate goal now. So we have to do some technical steps, and for this reason we are proving these lemmas. So do you have any questions on the proofs? Well, then let me turn off my microphone, but if some questions still come to your mind, you can just ask, and I'm here, so I will switch on back my microphone and reply to your questions. So now we still have around 7 minutes for the break. Let's make this break. Okay, I think we can proceed. Now I'm going to prove lemma 3. Let me recall lemma 3. So it says that for any, so given a G-invariant valuation V, and given a rational function f with B-stable poles, there always exists a B semi-invariant rational function, f tilde, which has on which V takes the same value, and the values of all other G-invariant valuations, say V prime, are greater or equal than the values on F. And also the same holds for valuations corresponding to all B-stable prime divisors of X. So this is what lemma 3 says. Now let's turn to the proof. First, without loss of generality, we may assume that X is smooth, because, well, X is always assumed to be normal, and we can remove the singularities. The singularities are of codimension at least 2. So removing something of codimension 2 does not change divisors, does not essentially change prime divisors. So we may assume that X is just smooth. Now, the complement of the open Borel orbit y upper naught in X is the union of finitely many B-stable prime divisors. This we already explained. So this D1, etc., Dm are B-stable prime divisors. The only B-stable prime divisors which are on X, because they all sit in the complement of the open B orbit. B-stable prime divisors. So this is this picture. Okay. Now let's consider the following divisor, denoted by delta, which is minus the sum of these di's with the coefficients which are the orders of vanishing orders of f along di's. So we take these divisors di's with the coefficients equal to the vanishing order of f with the minus sign, like this. Since X is already smooth, this divisor is Cartier. And therefore, it defines a line bundle over X and the canonical rational section S sub delta, canonical rational section.
So how can we assume? Why can we assume X is smooth?
Just by removing the singularities, because singularities are small. X is normal.
We just take the complement of singularities, right?
Yes. We take the smooth locus of X. We replace X with its smooth locus. And the divisors remain unchanged. So you just remove something of smaller dimension. So we get this Cartier divisor, we get a canonical rational section of the respective line bundle whose divisor is exactly delta. Canonical rational section of the line bundle O of delta. And now, if we take yet another section, so put S be this canonical section multiplied by F, by my rational function F. which we started with, what we get? We see that multiplying f by s delta kills all poles of f, because if you have a pole of f along some di, then this di, this vanishing order is negative on f. When you multiply by delta, by s delta, so you make this coefficient equal to 0, because the divisor of f contains di with the coefficient equal to this vanishing order, equal to this number. And when you multiply by this rational section, you just add the same number with the sign minus. So the coefficient will be 0. So finally, this section S will have no poles. It will be a regular section. And even more, the vanishing order of S along each of these b-stable prime divisors will be 0. So S will have neither poles nor zeros along b-stable prime divisors. This is just from the definition. Okay? What we do now? Now we mimic the affinization construction. So we take this X.
Well, how do you define a canonical rational structure?
Well, I mean, some time ago, I discussed the relation between Cartier divisors, line bundles, and their sections.
I know, but I don't think the construction is canonical.
Well, it is canonical up to isomorphism. I mean, up to isomorphism, of course. If you have another line bundle isomorphic to this one, and another section, another rational section of this line bundle with the same divisor delta, then there is an isomorphism between these line bundles, which takes one section to another one.
The quotient of these two bundle or two sections is a regular function.
The quotient is a nowhere vanishing regular function.
Yes, I know where I remember.
Mm-hmm. Okay, so what we do now? So we have this X, and let us consider a version of the punctured affine cone over X. So let me denote it as X hat. It is just the total space of the dual line bundle, the total space of the dual line bundle corresponding to the divisor minus delta with the zero section removed, minus the zero section. And we have a projection map from this X hat onto X. So let me again show you the picture. So you have this X, and you have the fibers of the dual line bundle. Over X, the fibers of the dual line bundle over X. But we remove the origin. We remove the origin from each fiber. We remove the zero section. So this is more or less the same as the punctured cone over X. In the punctured cone construction, we take the line bundle O of 1 instead of O of delta. So in the classical affinization construction, this delta was a very ample divisor, and this O of delta was just O of 1. And the dual line bundle is the tautological line bundle over the projective space. So when we take this X hat, we take just the cone over X in this case. And this is a bit more general, but it is not essential for our proof. What is essential is that we have the pullback inclusion of function field of function fields. So the function field of x is embedded in the function field of x hat in an obvious way. And the sections which we considered before, so this S and S delta, they are rational sections of O of delta of this line bundle. S is even a regular section, but this doesn't matter. They are rational sections, and rational sections of O of delta can be viewed as functions on the total space of the dual line bundle. The functions which are fiber-wise linear. So, in other words, these sections can be regarded as elements in this function field. Okay. Now, what we do, we have G-invariant valuations on this function field. We have G-invariant valuations on this function field. Say V, V prime, etc. Many G-invariant valuations. And by what we already discussed before, we can extend each of these G-invariant valuations to invariant valuations on this bigger field. They will be invariant, maybe not under G, but under G prime, which is a finite cover of G. We have already used this notation, so I will not repeat it. So we can extend this V, V prime, etc. to G invariant, G prime invariant valuations of this bigger field. And here we use lemma. Here we use lemma 2, because the first thing we do, we extend these valuations to maybe non-invariant valuations of this bigger field. This bigger field is actually a pure transcendental extension of this field. And we already discussed how to extend the valuation from here to here to a pure transcendental extension of degree 1. When we discussed the affinization construction in the proof of lemma 1 on the previous lecture. Okay. So first thing we do, we extend these valuations to non-invariant valuations on this bigger field. And now we apply lemma 2 to replace them by G prime invariant valuations. So here we apply lemma 2. Let me write it explicitly. Here we apply lemma 2. Okay. So in other words, we may consider the values of these valuations V, V prime, etc., which were initially defined on the function field of X. We may consider the values of these valuations on sections of this line bundle O of delta. Okay. And now what we do? So let's consider again the linear span of the G orbit of the section S in the space of global sections of my line bundle. Let me denote it again by M. This is a finite dimensional G module, and by the multiplicity-free property, it decomposes uniquely as a sum of pairwise non-isomorphic simple G submodules, which I denote as M sub lambda i's, lambda j's maybe in brackets. Okay, with respect to this decomposition, we have a decomposition of S in a sum of Sj's, where each Sj is a non-zero vector in one of these submodules. Okay. So now in this setting here we are already I would say in the quasi-affine case, and well, maybe not in the quasi-affine case, but in this setting we already proved in a bit different context, but the proof will be the same, that the value of V at S is just the minimum of the values of V at Sj's. And we may assume that this minimum is achieved for J equal to...
yes? How can we deduce that Sj is not zero, or we just choose a non-zero term?
Well, you may say we choose non-zero terms, but actually this is because of this formula, because M is spanned by the orbit of S. So if sum of these projections is zero, then this term will not occur in this linear span. This sum will not occur in this linear span. Okay. So
is the global section of no yes I know.
Okay.
No problem.
Great. So now we have this formula which we proved previously for values on regular functions, but for sections it will be the same. That because sections are regular functions on the total space on this X hat, by the way. So we can apply what we did before in the quasi-affine case. So we have this formula for the value of V on S, and we may assume that this minimum is achieved on J equal to 1. Say this equals to V of S1. So without loss of generality. Okay. Now let's take for S tilde the highest weight vector of weight lambda 1 in this first direct summand corresponding to the highest weight lambda 1. This will be S tilde. So S tilde sits in the same simple submodule as S1, but it is the highest weight vector in this simple submodule. Then we have that the value of V on S tilde is the same as the value of V on S1, because the G-invariant valuation V takes one and the same value on all vectors in an irreducible submodule, on all non-zero vectors in an irreducible submodule. This we discussed on the previous lecture. Okay, and this is the same as V of S by the above. While for any other G-invariant valuation, say for V prime, again, the value of V prime on S tilde is the same as the value of V prime on S1. But now this value is greater or equal than the value of V prime at S, because the value at S is the minimum of these values. So this may be greater or equal.
Okay, so also, which is the highest weight vector?
S tilde is the highest weight vector in this irreducible submodule of highest weight lambda 1.
Oh, we choose S tilde, right?
Yeah. We choose take S tilde to be the highest weight vector.
So why is the value of S tilde is the value of S?
Well, this we discussed on the previous lecture when we considered the values of a G-invariant valuation on the coordinate algebra of a spherical variety. we said that the value on each irreducible summand will be constant.
Yes, I know that. I mean, I know. Thanks.
Okay, good. So we have these two formula, and also for any b-stable prime divisor D, or maybe di's, we have this notation di's, we have that the vanishing order of S tilde along each of these di's is greater or equal than 0 because S tilde is a regular section. So we have this formula for S tilde, and now it remains to put F tilde equal to the ratio S tilde over S delta. Then let me also recall that by construction, our initial F is the ratio of S over S delta. Now it is easy to see that this F tilde satisfies all statements of lemma 3. I mean, all these three properties. Just because it differs from F tilde differs from F by this numerator of this fraction. We replace S with S tilde, and when we replace S with S tilde, this value will be the same, and these values will increase. Yeah. So this ends the proof. This finishes the proof of lemma 3.
Sorry, I have a question.
Yes.
So how can you define the valuation on sections?
Let me again come back to the previous page. So we did this by extension of initial valuations on this field to this bigger field.
In the function case, I think we can embed the ring of regular functions in the field of rational functions. Then we take a restriction.
Here we consider rational functions, not just regular. Here we consider rational functions, and we have the valuations v prime, etc. on this field, and we extend these valuations to invariant valuations on this bigger field.
Okay.
So this extension is possible by in the same way as on the previous lecture, when I extended valuations from X to the affine cone over X.
Okay.
And this X hat is more or less the same as the affine cone. This is the total space of a line bundle over X with zero section removed. So we extend these valuations, and then we apply lemma 2 to make these extended variations invariant. So here we apply lemma 2.
This is not the problem. So why the sections? Maybe the ring of sections. Why this ring is embedded into
the section is considered as rational functions on X hat.
Exactly.
So we can take the valuation of the sections.
Exactly. The section any section of this line bundle can be considered as a fiber-wise linear function on this guide.
Okay.
So sections may be regarded as functions on this variety. Okay.
Okay. Thanks.
Good. So we have finished the proof of lemma 3, and finally this concludes this fills all gaps in the proof of lemma 1. So all lemmas are proven. Yes.
Oh, so the value of F tilde is the value of S tilde is the subtraction of the value of S tilde from
Yes, yes, yes. When you take the ratio, then you subtract the values, the value of denominator from the value of the numerator. Of course, this is because of the multiplicative property of the valuation. The valuation is a group homomorphism from the multiplicative group of functions to the additive group of rational numbers. That's why we subtract the values, exactly. Okay? Well, so we explained that G-invariant valuations are uniquely determined by linear functions on the weight lattice. And for this reason, let me turn to the next page. For this reason, we may identify a G-invariant valuation, say V, with the respective linear function, which I denoted by V bar. So we shall not write bar in the sequel. We just write V instead of V bar. So,
Professor, come back to the proof of lemma 3. How can we deduce that for the order of S tilde is non-negative also?
Because S tilde is a regular section, yes.
So we have that
because of that, and because of
well, how can this conclude that the condition 3 of lemma 3?
So because of what I'm writing now. Okay. Let me recall that this section S has the property that it has neither zeros nor poles along the i's. And now we have the same inequality as on the previous line.
And how does F tilde G invariant?
Say it again. What about F tilde?
F tilde is B semi-invariant.
Exactly. It is B semi-invariant because both numerator and denominator of this fraction are semi-invariant.
I know that S tilde is B semi-invariant, but how does S tilde the denominator?
Yeah. Just because the divisor of S delta is B stable, because S delta has the divisor delta, and this divisor is B stable. So this divisor is B stable.
I know.
Okay. So more questions on this lemma, on the proof of this lemma so far? Well, let's go on. So since we may identify a G-invariant valuation with the respective linear function, we shall write V instead of V bar. So we shall write like this, that V itself is a linear function on the weight lattice, so belongs to the space of linear functions on the weight lattice with values in Q, which is of course the same as the dual lattice lambda sub x star tensor with Q over Z. And this vector space over rational numbers I will denote by script E sub x. So this is a Q vector space spanned by the dual of the weight lattice. And in this space, there sit the linear functions corresponding to valuations, in particular corresponding to G-invariant valuations. And now there arises a question. Which linear functions, which vectors in this vector space E sub x indeed correspond to G-invariant valuations. So how to describe the vectors corresponding to G-invariant valuations in this vector subspace, in this vector space? The next lemma gives an answer to this question. So lemma 4 says that G-invariant valuations regarded as vectors in this vector space E sub x, G-invariant valuations of the function field of my spherical variety x, form a solid convex cone in this vector space. Let me denote this cone as script V sub x. This cone is called the valuation cone. So the valuation cone is the cone consisting of all linear functions on the weight lattice, which correspond to G-invariant valuations of the function field of x. And since we know that G-invariant valuations are uniquely determined by these linear functions, we may regard the points in this cone as valuations on x, as G-invariant valuations on x. So my next goal is to prove this lemma. Again, it is easier to handle the quasi-affine case.
Professor,
yes?
Sorry. I think I have a problem about the proof of lemma 3. About
yes.
the condition 3 of the proof of lemma 3. I mean, the order of di at s tilde is greater than the order of di at s. So this does not depend on the extension of the valuation at di, right? Just
yes, this does not depend, because we do not extend valuations. Well, you may say we extend these valuations in a canonical way. So we do not extend valuations corresponding to di's. We extend G-invariant valuations on this function field, which maybe do not correspond to any divisors on x. If you have a divisor on x, then the valuation corresponding to this divisor is canonically extended to this space, because you have a canonical way to define what is the vanishing order of a section along a divisor. We have discussed this when we spoke about sections, line bundles, and so on, and whatever. So these valuations corresponding to di's are already canonically extended to sections. And for these valuations, V, V prime, and so on, we have no canonical extension. We have to construct such an extension, and we do this here. Okay?
Okay.
Good. So let's turn back to the proof of lemma 4. So we start with the quasi.
So by solid, you mean that this cone is of maximal dimension. The same
yes. Let me to avoid confusion, let me write this explicitly of full dimension, I would say, like this, of full dimension, of the same dimension as this vector space E sub x.
So this is only available for spherical variety, yes.
You can formulate more general things. I mean, this whole business on G-invariant valuations can be extended to non-spherical varieties, but the formulations will be more complicated, and I don't need this because I'm concentrated on spherical varieties. Yeah. So in the quasi-affine case, let us take any G-invariant valuation V of my function field. And let us analyze the respective linear function, the respective vector in this vector space E sub x. So consider two irreducible submodules in the coordinate algebra of x. Say k of, maybe I will write it a little bit more on the left. Say k of x sub lambda in brackets and k of x sub mu in brackets. And let's consider the product of these two irreducible submodules in the coordinate algebra of x. Well, when I speak about such kind of products, I always mean the respective linear subspace. This means that I take the linear span of all products, the linear span of all products of elements from here and elements from here. So this product sign means linear span of all products. So this is a vector subspace, a G-stable vector subspace in the coordinate algebra of x. So this product subspace is a homomorphic image of the tensor product. A homomorphic.
So the two space, the product is the usual product of polynomial.
Usual product, yes. Usual product in this coordinate algebra. Usual product in K of x. But we also take the linear span of all products from here and here. Okay.
Yes. So well, the right lower corner lambda is for what?
Highest weight. Lambda is the highest weight of the irreducible submodule. So this was our notation. K of x sub lambda in brackets was our notation for the irreducible, for the unique irreducible submodule in K of x of highest weight lambda.
Since x is spherical.
Yeah. X is always spherical. Yeah, x is always spherical. So let me repeat that this product subspace is the homomorphic image of the tensor product of two irreducible G modules V of lambda and V of mu. Homomorphic image. And if we look at this tensor product and look at the T eigenvectors in this tensor product, then we'll immediately see that all T eigenweights here are of the following form: lambda plus mu minus several positive roots. So all T eigenweights in this tensor product are of this form. This is because, well, some time ago we proved a lemma about T eigenweights in an irreducible G module of highest weight lambda. This lemma said, or maybe this was not lemma, just observation. This statement said that all T eigenweights in here are obtained from lambda by subtracting several positive roots. And when we take T eigenweights here and T eigenweights here and take tensor product, then the eigenweights just add. So T eigenweights in the tensor product are of this form. And the weight lambda plus mu occurs only once. It is the eigenweight of the tensor product of the highest weight vector in here and the highest weight vector in here. So since
alpha I can there may occur the same alpha I, right?
Yes, yes, of course. They may repeat. They may occur repetitively. So this means in particular that when you decompose this tensor product as the sum of irreducible G modules, then this will be isomorphic to this summand. We have this summand V of lambda plus mu with multiplicity 1, and also some other irreducible submodules whose highest weights are of the form lambda plus mu minus some beta j minus beta 1 plus etc. plus V of lambda plus mu minus beta s, where these beta j's are sums of positive roots. Okay, so this is how the decomposition of the tensor product of two irreducible G modules looks like. It has an irreducible submodule of weight lambda plus mu with multiplicity 1, and also there occur some other irreducible submodules, maybe with positive multiplicities, with multiplicities bigger than 1, whose highest weights are smaller than lambda plus mu in a sense. They are obtained from lambda plus mu by subtracting sums of positive roots. So this is the decomposition for the tensor product. And when you take the homomorphic image, then just some of these summands map to 0. So the decomposition of this tensor product into irreducible G submodules will be of the following form. We have this space K of X sub lambda plus mu, and also some of the spaces K of X sub lambda plus mu minus beta j, but maybe not all of them. Maybe, well, after renumbering, you may assume that the first R summands occur in this decomposition. So the last one will be K of X sub lambda plus mu minus beta R. Okay? Where R is less or equal than C. And the remaining beta j's, the remaining summands with j bigger than R will not occur. They will map to 0 under this homomorphism. Okay. So we have this form of the decomposition of the product of two irreducible G submodules in the coordinate algebra of X. Now, if we take, well, maybe let's turn to the next page. If we take sufficiently general vectors f in K of X.
Hey, Professor.
Yes, sub lambda.
About the previous page.
Yes.
So, how can we deduce that the space V lambda plus mu does not map to 0?
Good question. I expected this question. Thank you for this question. Let me reply. So let me say that what is maybe I will do it on the next page. There is more room on the next page, so this I will shift to the bottom. So what is V of lambda? V of lambda can be realized as the space of global sections of a line bundle over the generalized flag variety. G over B, the line bundle corresponding to the character minus lambda star. Lambda star is the highest weight of the dual module, okay? And the same for V of mu. Okay? And also the same for V of lambda plus mu. Now, when we consider the tensor product of these two vector spaces and project onto here with respect to this decomposition below, we can project the tensor product onto this summand. Such a projection is unique up to a multiple by Schur's lemma. So in the language of sections of line bundles, this projection is just the tensor product of sections. This is just the tensor product of sections. Because this line bundle is just the tensor product of the previous two. If you have two non-zero sections, then their tensor product will also be non-zero, because so if you have this, say, a section S here and a section say T here, then non-zero. Then the tensor product will also be non-zero. This is because, well, this is more or less obvious, because since both sections are non-zero, they do not vanish at one and the same point. They do not vanish at some open subset, and if we take a point in this open subset, then we get a point at which both sections do not vanish, and then the tensor product also does not vanish at this point. What does it give you for your question? This means that when you take a tensor product of two vectors from here and from here, and project of two non-zero vectors from here and here, and project onto this first summand, this projection will be always non-zero. And when you pass from the tensor product to the product in the coordinate algebra, this tensor product will be replaced just by the usual product of functions. So this homomorphism from the bottom to the top, this homomorphism maps tensor products to products. And by what I said before, the projection of the product of two non-zero functions from here and here onto this summand will always be non-zero. Okay? Did I answer?
Yes, I know. Well, we use the fact that the coordinate algebra over X is a domain without zero divisors, right?
Well, even not this. We just use we just use this representation theoretic observation that tensor products here correspond to products here.
Well, but if we have zero divisors in the coordinate algebra of X, then the tensor product is not like will be far.
Well. Yeah. I mean, you are right. You are right in the sense that you have to assume that this whole product is non-zero. Yes, because it may happen if your coordinate algebra had zero divisors, that it might happen that the whole product will be zero. So there will be no summons at all here. But if the sum of these summons occur, then actually these projections must be non-zero.
Oh, because it is generated by the product, and any product belongs to the first summon.
No. I mean, the product doesn't belong to the first summon. The product belongs to several summons, but the projection.
I mean the pure product. One choose from the first factor and one choose from the second factor. The product of these two belongs to the first summon. I mean,
yeah. By the way, yes. By the way, in here, there sits the highest weight vector V sub F sub lambda plus mu, which is just the product of F lambda and F mu in my previous notation for semi-invariant functions. So this F lambda, F mu, and F lambda plus mu are semi-invariant functions. And since, yeah, you are right, since your algebra is an integral domain, this product is non-zero. And that's why this summand occurs. And since it occurs, so the projection of any non-zero of the product of any non-zero factors from here and here will have also non-zero projection to here. Okay, so I see that it's time to finish. So let me finish at least maybe the main step of the proof of lemma 4. I will say some concluding remarks on the next lecture. But so this was a digression about tensor product. And let me now say that, if you take sufficiently general vectors from this irreducible submodule and this irreducible submodule, take sufficiently general, then the product of these two functions will decompose as the sum like this: h naught plus h1 plus etc. plus hr with respect to this previous decomposition, with respect to this decomposition of the product, so that each of the hj's belong to the respective summand k of x sub lambda plus mu minus beta j's. And also, if you take f and g sufficiently general, then all these projections h sub j's will be non-zero. And therefore, the value of my invariant valuation v on the product of these two functions f and j, well, since it is a valuation, it must be equal to the sum v of f plus v of j. Since f is taken from the irreducible submodule of highest weight lambda, the first summand will be the pairing of v, better to say v bar, but we agreed not to write a bar. a pairing of V with lambda, and the second summand will be the pairing of V with mu. This is on one side. And on the other side, we know that the value of an invariant valuation on the sum of this kind is the minimal value, of the values of V on the summands themselves, of V of HJs, which is the same. Let me write it maybe on the next line, which is the same as the minimum of the following set, the pairing of V with lambda plus mu, the pairing of V with lambda plus mu minus beta 1, and so on. The last element will be the pairing of V with lambda plus mu minus beta r. So the minimum of these values should be equal to this value, that is to the first element in this set. And this implies, of course, that the value of V on all these beta i's should be less or equal than 0 for any j of beta j's, for any j from 1 to r. And actually this should hold for any lambda and mu, such that the respective submodules occur in the decomposition of the coordinate algebra of X. So this gives you inequalities on the vector V, which are necessary for V to define a G-invariant valuations. So we may consider the cone. Let's consider the cone. This will be our V sub X. The cone defined by these inequalities. So consisting of all vectors V in the vector space E sub X, satisfying the inequalities like above. For all these beta i's, well, by the way, these beta i's are sometimes called tails. These beta i's are called tails. So for all tails, beta j. This gives you a set of linear inequalities defining.
Professor, I think the tails is relative to lambda and mu.
Exactly.
So when we choose tails, we exhaust every lambda and mu.
Right. We choose all tails for all pairs of lambda and mu. So let me write here that you also take all lambda and mu. So this set of linear inequalities defines a cone in the vector space E sub X, and it is necessary for V to define a G-invariant valuation. It is necessary to belong to this cone for V to define a G-invariant valuation. This condition is also sufficient, but let me finish the discussion on the next lecture, because now I am over. My time is over. I am over my time, or even 9 minutes over my time. I'm sorry for that. So let me stop here and let me finish the discussion of this lemma on the beginning of the next lecture. So this cone will be exactly the valuation cone of my spherical variety X. Thank you for your attention, and sorry for taking your time. But this, I'm sorry, but still, this is because I answered questions. I hope that it's okay to answer questions during the lecture. Makes the exposition more clear. So this also takes some time. Sorry for that. Thank you. So if you still have any questions, then please ask your questions.
I have questions. Well,
yes,
about the proof of lemma 3. Again.
Coming back to the proof of lemma 3. Okay, let's come back there.
Well, about the B semi-invariance of F tilde. Well, you mean S tilde and S delta are both B semi-invariant, right?
Exactly.
Well, both. But I look through the construction of S tilde. Well, the construction of S tilde consists of pasting different locally trivial sections via the transition functions, right?
So actually, I would say I didn't give you any construction of S delta. In fact, I just said when we discussed Cartier divisors and line bundles, I just said that any Cartier divisor corresponds to a line bundle.
You said that it does any Cartier divisor does correspond to a unique line bundle and specified rational sections for this Cartier divisor and the and the line bundle and the section are unique up to isomorphism. I mean, you indeed say that. But if we multiply S delta by a nowhere vanishing regular function, do we get another specified line bundle and S delta and a section?
How to say? Well, yeah, I understand your question. So in principle,
I mean, if any multiplication of S delta and a non-zero regular function is again a rational section that corresponds to the Cartier divisor. So how can we deduce that S delta is B invariant since the nowhere vanishing regular function may not be B semi-invariant, I think.
Well, actually, let me say, let me give you a precise statement. Well, actually, it will be a B semi-invariant in this setting. But
if the any two specified rational section differed by a B semi-invariant regular function, then the construction of the rational section will matter because otherwise we can choose any function to multiply the rational section.
Let me reply. So so in our situation, X is acted on by G and therefore by B. So X is a B variety. Yeah.
Yes.
So B acts on X. Yeah. And so the claim is that actually any nowhere vanishing function on X is B semi-invariant. So if F is invertible on X, F is invertible, then this implies that F is B semi-invariant. Let me explain why briefly. So the reason is the following. So let us compactify X. We can embed X in a project, well, in a complete or even projective variety X bar. Projective, on which B still acts. So it is possible to compactify X B equivariantly, even G equivariantly. Maybe I could here put G. We'll discuss this kind of things a little bit later. I'm not sure. Sorry. I'm not sure I will prove this general fact, but this is true. If you have a G variety, you can compactify it in a G equivariant way. So now X bar is projective. And since your function is invertible on X, its divisor on X bar, so we can write somewhere here the divisor of X of F on X bar is contained in the complement, in the boundary of X, yeah?
Yes.
Like this. And this means that this divisor is B stable.
Yes.
In particular, even G stable, B stable. Now, if you act on F by an element from B, so if you consider this function BF, then the divisor will be the same.
Yes. Oh, and nowhere vanishing regular function on a complete variety, yeah, is always constant, right?
Exactly. This is the reason.
Oh,
so this is the argument.
Oh, so every different pair of S delta differ by B semi-invariant function. So S delta itself is B semi-invariant.
Right.
Thanks.
You are welcome. So more questions? Well, still you are welcome to address your questions to me on email. I will reply. And also some of you already sent me your homeworks, solutions of exercises. I'm sorry I didn't have time to reply on the weekend, but I will reply today. So by the time difference, you will receive my answers maybe tomorrow on Tuesday. I will check your solutions and answer your questions. Well, if there are no more questions so far, then maybe I can stop sharing the whiteboard. No questions? Good. And see you on Wednesday. So,
okay.
Goodbye. Thank you.
Bye. Thank you for the lecture. Yeah.
Bye-bye.